Hi friends, let's have a look at today's daily challenge problem. Problem 921, minimum add to make parentheses valid. This is a very routine problem. So typically for this this kind of problem related to valid parentheses, we can think of the stack data structure. So though you can choose to use stack explicitly or implicitly, essentially stacks plays a role in such problems. So here we are going to do this problem, and in the next video we are going to do some related problem to this one. So in the statement of the problem, it first defines what is a valid parentheses string, and then we want to find the minimum number of moves required to make a given parentheses string as valid. So here in one move, we can insert a parenthesis at any position of the string. So by the definition of the move, actually, in order to process with this problem, we just need to monitor or track how many unmatched open parentheses and how many unmatched close parentheses. Then we just return the sum of those two. That will be the result. So let's look at the two examples. So actually, this two example is not still not very representative. So the first one is something like this. We have something like this, right? So notice that the first two parentheses forms one valid one. So it has one closed parenthesis extra. So the return would be 1. And in the second one, for sure, so you know, there are 3 open ones, so 0 closed ones. So we return 3 for this one. So actually, the main point for this problem is the definition of this move, right? So in one move, we can insert a parenthesis at any position of the string. Because of this one, you can insert at any position. You can insert open parentheses or close parentheses at any position. So as long as you have one extra open, so you can just add, follow the open one, the closed one, then it will make it balanced. As long as you have a closed one, you can add a open one, right? So this seems trivial statement. However, this is the very point of this problem. So we can write code so that we can track the extra open parentheses and the extra close parentheses, and then we just return the sum. So here also, if you look at the constraints of the problem, so the length of S is bounded above by 1000, which is not very large. In other words, this number basically quantifies the problem size. So the SI is either open parentheses or close parentheses. So with that said, and we can look at the code, and then we can maybe, if needed, we can also go over a extra example. First, I'm going to introduce a variable called extra. So this will track the extra close parentheses. And also, I'm going to use a stack to track the extra open parentheses. So here we explicitly use using stack data structure. However, we can modify the code so that we implicitly use this one. So now basically it's a standard for loop. So for character in S, right? So if character is an open one, right? So in this case, we are going to put this one in the top of the stack. So we're going to do stack append character. So otherwise, if the character is a closing factor parenthesis, we're going to check if the stack is empty. So if it's not empty, so we're going to pop one open parenthesis to make it balanced with the current close parenthesis. So in other words, if stack, so we're going to do stack pop, right? Matching a pair, right? Here it's matching a pair. So otherwise, so the stack's empty. So we still have extra closed ones. It looks like something. You have some ones like all balanced, right? Then you have an extra closed one. So it's like something, just a single one, right? Then you are going to increment the extra by 1. So increment by 1, right? So with that done, so actually afterwards, so we can check the extra and the length of the stack. If the length of the stack will be the extra open parentheses, right? So what we are going to return will be return the length of stack plus the number of extra close parentheses. So this number is the minimum number of moves required to make the S balanced or valid. Let's do a quick test. It passes 1, and now let's submit that. It passes all the cases. So now if we want to do another example, you can create one. For example, this one. You write some more, right? Let's see. It's 11, so because it's too long. But if you prefer to add some finer details, you can do a detailed walkthrough, or you can print some information in the for loop so that you can track the procedure. So this is the one way that we explicitly using stack, right? So now we can actually implicitly using stack. Let me copy this part, and then I'm show you how to modify the code. So I'm going to change this one to be version v1, and then notice that the stack actually stores only open parentheses. So in other words, the counting is important. So I'm going to like say n open, right? Extra open. So it's 0, right? So now if a character is s, so we are not going to put the character into the stack. So now we are going to do n open increment by 1. So this is corresponding to do the stack append operation, right? And then otherwise, so if stack is not empty, it means that if n open is greater than 0, right? So that's in correspondence. Then in order for pop, so we're going to decrement this by 1, right? This corresponds to the pop operation. Otherwise, we do extra plus 1. So now we have the extra open ones and the extra closed ones. So we just need to return the sum of those two. So let's do a test and submit that. Yeah. So I guess so this let me change this one to be implicitly using stack. So overall, as a recipe for those this kind of problem is that when you check balance or do some deletions or adds for this kind of problem, you can think of stack data structure. So with that said, I guess that's about it for the current problem. Thank you.